Right, hello everybody. Because I've been unable to give lectures for the last couple of weeks, I haven't been able to explain in the lectures something I wanted to explain, and so instead I'm recording this video to hopefully give an opportunity to see this information. And the purpose of the video is to help you program more advanced artificial intelligence for your game playing programs. So hopefully this will be useful for your programs playing Capture Go for the competition in 2 weeks' time. And for those of you who are going to implement Go, the actual game of Go for the final project, it should also be useful for that. So the presentation is going to be divided into 2 parts. Firstly, I'm going to assume that you're at the stage that you've got a basic minimax or alphabeta algorithm running and playing the game, and we're going to look at ways of improving that. And then the second half, I'm going to introduce a wholly different approach to game playing intelligence, which is an algorithm known as Monte Carlo Tree Search, which is a very powerful and general algorithm for artificial intelligence for game playing programs. Okay, well, we'll start with the first part of improving minimax and alpha beta algorithms. And so assuming you've got a basic minimax or alpha beta algorithm programmed, my application doesn't seem to want to settle on the right page, but here we are. Then what can we do to improve the performance of your algorithm? So how do we improve minimax or alpha beta? And there are going to be a number of suggestions here of things you can do. You can do some of them and not all of them, or you might have other improvements of your own. But anyway, this is what I did to these suggestions are the various things I did to improve my own program for playing Capture Go. So the first one is just as a basic start, use alpha beta instead of minimax. The algorithms are equivalent in terms of the result is essentially they both perform an alpha beta search up to whatever depth you specify. Only alpha beta, they both perform a minimax search up to whatever depth you specify. Only alpha beta is more efficient. Okay. So once you've done that, once you've got alpha beta, the next thing to do is to try and make it efficient as possible. So as you will remember from the lectures when we discussed minimax and alpha beta are searching the game tree of possible moves starting from the current position. You're the player and you're playing against an opponent. You look at all the moves you as player can make, and then all the moves that the opponent can make to all the moves that you can make, and then all the responses that you as player can give to all the moves that the opponent has made in reaction to the moves that you have made, and so on. And in general, you'll set some depth and you'll search the tree up to a particular depth. But each time you're searching from the current game position to the in the tree to all the possible children nodes in the tree corresponding to the moves you can make, from the current position, you need to compute the possible moves from the current position. And because this is going to be done thousands of times over, because you're searching an absolutely huge tree, you want this computing the next moves from a current position to be as efficient as possible. So I just want to say there are essentially two different styles of approach you could adopt here, and it's up to you which one you adopt, and you can experiment in practice to see which one's more efficient. One is to simply do a for loop going through the board positions. So here we've got the the index of the x coordinate I and the index of the y coordinate j, and we're counting through from 0 up to and including 8 in both cases. So this should be a second plus on the j there, as we're incrementing the j. Let's make that clear. And a move is possible if we're playing, say, capture go, if the intersection on the board at coordinates ij is empty. So you can simply test that, and then you get the list of possible moves. Okay, that's the easiest thing to do. An alternative that may be more efficient, particularly if you want to then build on it to consider some of the other modifications that are going to follow later, is instead of all the time going through this double for loop, which is always checking 81 positions on the board, another possibility is to maintain a set of possible moves, možné potéze, I'm calling this, as a field in your igre class. So every igre object will have, as part of it, a field možné potéze, and that možné potéze will contain a set, which could be implemented in any of the Java ways you like of having a set. For example, a hash set would be one way of doing it. And then you simply have, or when you're in a game position, you simply have the list of possible moves available, and you don't need to do a double nested for loop through the 81 different positions on the game. Okay, that's a very small modification, but once you've got something like that, you can go on to do I'm afraid my program with the board on it is not behaving very nicely because my computer is doing so much, because it's running because I'm doing the video recording actually via Zoom. Anyway, never mind. So once you've got a list of possible moves like that, there are ways of modifying that mean that you're looking at fewer moves in general. So a particularly obvious one is to compute a list of, well, what in English I would call forced moves. The nulné potéze is kind of sort of urgent moves or essential moves. I don't know if that's the best translation in Slovene here, but the point is, from your current game position, compute a list of moves which are forced to be made as the next move if such moves exist. And the kinds of things I have in mind, essentially two examples. So these would both be forced moves for black. So one is if black is in a position in which there's some group of blacks here that has only one liberty to it, only one means of escape, so that if that position is left empty for white to play in, white will win the game by taking it. And then I would call that a forced move, because if black does not play that move, black will die. Black will lose the game. So that's one example of a forced move. And another example of a forced move is, well, it's not really forced, but a move that black might as well make rather than making any other move. Black's not going to lose anything by making this move, because in fact it's going to win the game. So if black actually has a move available by which they're going to take white's piece in the game of capture go, well, then they win the game, so they might as well make that move now. So the point is that if one calculates a list of forced moves from a current position, if any forced moves exist, well, there's absolutely no need for the minimax or alpha beta search to consider any other moves from that position, because if we're calculating the move for go, black might as well play a forced move. So we only need to consider the forced move. So that cuts down the branching considerably when one is of the tree search, when one is in a position from which forced moves exist. So having done that, the next observation, oops, it's really frustrating. If I try to scroll, it just runs away with me. So anyway, once we've got a list of forced moves, well, forced moves shouldn't really have any effect on the depth of the search. So I've drawn a little illustrative example in order to show what I mean by this. So suppose we're doing a minimax or alpha beta search to depth 2. And so what we would normally do is we look at its green's go to play here. So we look at all possible moves that green can make. And then for each possible move that the opponent, red, can make, we look at all possible moves that they can make. And normally at depth 2, we would stop the search there. But if there's any position at which there is what I'm calling a nuna potesa, so a forced move, then there's not going to be any branching from that position, at least if there's only one forced move, which is normally the case. You can think about the combinatorics of when there can exist more than one forced move and what the ramifications of those combinatorics are, if you like. But anyway, the usual situation is if there's just one forced move. So of course, if there's a forced move, if there's a single forced move, then the search from here might as well just look at that branch and doesn't contribute to the branching of the tree. So you might as well just count that as part and parcel of the previous move in terms of searching the depth. The point of limiting the depth is to avoid the explosion in having too many moves to look at and running out of time in the search for the minimax or alpha beta search. But here this move was forced, so we might as well not count that in the depth. And so for a depth 2 search, when there's a single forced move, we can skip that when we count the depth, and we can go to the next depth. It's a very small saving here, but if forced moves happen early on in the search, or if there's a chain of forced moves in the search, this can considerably extend the effective depth of part of the search. And in particular, it allows the minimax algorithm on a low depth, in order to avoid a combinatorial explosion, to find out what the consequences are of chains of forced moves, which is often an important situation to know, to avoid, to be able to avoid in a game playing. You don't want to get into a situation where your opponent is going to be able to have a sequence of, give you a sequence of forced moves that will in the end force you into a bad position. So something else I've incorporated in my algorithm for minimax, well, my alpha beta algorithm. I keep on saying minimax because minimax is what one usually says to describe this kind of algorithm, but I always now specifically mean alpha beta because I've implemented the more efficient version, which is alpha beta. So in my algorithm, well, there's what you want to do is to be able to set the depth for the minimax or alpha beta search to be as large as possible, to have as deep a search as possible, so that your computer player does not take more time than is allowed. And in the case of the competition that we're having in 2 weeks' time, the amount of time allowed is roughly 5 seconds per move. So I've written this down as 5 plus epsilon seconds. One's allowed to go a little bit of an epsilon over 5 seconds, but I'll tell you a little bit more about how that's done, how that's going to be done later when we look at the program running. So in order to do that, well, what search you can do is going to depend on how many moves are available in the game. At the start of the game, when there are 81 moves available for the first move, and a similar number of moves for the early moves, the possible depth of the search is going to be quite low, because at each move the tree is branching by, ignoring force moves, the tree is branching by roughly 70 to 80, a factor of 70 to 80. So in my algorithm, I can set the depth. In order to have the algorithm work within 5 seconds, I can set alpha beta to a depth of 4 at the start of the game. But as the game continues, the number of available moves decreases by 1 every time a move is played. And at some point in the game, you'll get to a level at which the branching is much less significant, and you'll be able to have a depth of 5, well, an increased depth over the depth you started with. And again, as the game continues, then eventually you'll get to a stage at which you'll be able to increase the depth yet again. And so what I've incorporated into my program is a rather crude estimate based on some estimating formula I have based on the number of moves that are available, what depth of alpha beta search my algorithm is able to do within 5 plus epsilon seconds from the position. So my alpha beta strategy actually adapts the depth as the game progresses, and the depth of the search gets deeper and deeper as the game goes on. Okay, something else that's useful to do, well, that's important to do in implementing the game, and you will have all needed to do this in order to be able to detect whether a game has been won or lost, is to implement an algorithm that calculates groups of stones and their, what are in English called their liberties, so the available, the escape places for a group of stones. So in this particular example here, we've got a group of 3 black stones connected together here, another group of 1 white stone connected, well, it's not connected because it's a single stone, and another group of 2 white stones connected together. And the black group has the liberties that are circled in yellow. So these are all the intersections that the black group can, that are adjacent to the black group. So there are 6 of those yellow circled intersections. The white group has the 2 intersections circled in green as its liberties, and the other white, so that this white stone, individual white stone, and the other white group of 2 has these 6 sort of light blue circled liberties available. So I think you will all, if you've implemented the game, have got to the situation where you've calculated such groups and their sets of liberties. But it is useful to be able to efficiently calculate these sets of liberties. Sorry, we've gone again. I think I just need to do the paging like this. I wonder if there's another way of paging with this software. That's the one we've just been through. So in my program, it's important to efficiently calculate these sets of liberties, because I actually use it use the sets of liberties for three different things. I use the sets of liberties to compute the status of the game, so whether the game has been finished, and if whether the game is completed, so, and if so, who has won and who has lost. I use the sets of liberties to calculate these sets of nune potesa, the forced moves, and I also use the sets of liberties as part of my alfabeta algorithm, as part of my algorithm that does the position evaluation. Part of the position evaluation, in fact, in my case, the whole position evaluation is based on the sets of liberties. So because I'm using it for three different things, one wants to avoid a situation in which every time you ask for the set of liberties, you recalculate the set of liberties from the current game position. That would be very wasteful, because calculating the groups and their sets of liberties is a reasonably computationally intensive class. It's a computationally intensive task. So what I recommend instead, and what I do in my program, is that you only calculate the sets of liberties once, and then you store the groups and their sets of liberties. You only calculate that once for every game position, and you store that information then in a field of the game class. So we're going to have a field of the game class that is the set of liberties. And in my program, I do that in the igre method. So when one makes a move in the game, at that point, you're always going to have to calculate the groups and their liberties anyway, because you're going to want to see, you're always going to want to see if the game position is won or lost. So at that point, you might as well do it when you first play the move in the game. You calculate the liberties in the groups and their liberties for the new game, and then store that information. So shranim rezultat, I've written here in Slovene, I hope that's okay. Store that in a field associated with the game object for your current position. And then when you want to use it for your stanje method that tells you what the current status of the game is, for calculating these forced moves and for evaluating the position, then rather than recalculating it, you have that you have that already, that you have the groups and the liberties already calculated for you, stored in a field in the igre object. And one other thing to say about calculating the groups and their liberties is that, as I said, that's quite a computationally intensive task. One way to do it would be to go over the whole game board, and so at every position, when you get into a new position, go over the whole game board and extract all the groups and their liberties. But that would be very inefficient, because when you make a move in a game, so you're changing from one position to the next, you're only making a very local change to the game. So you play a move in a game, and you're essentially only affecting what's local to the place that you've played the move in. And actually, the most efficient thing to do for calculating the groups and the liberties is to find a way of updating the previous groups and their liberties in the light of the new move you have played, with the so that based on the old groups and their liberties, you look at the new move you've made and you find a way of modifying the previous groups and their liberties to get the information of to calculate what the new groups and their liberties are there. Okay, and the last thing I want to say is that we want to have a good position evaluation, obviously, because whenever you're implementing minimax or alpha beta, you do search for as far as you can, but and you try to make that as efficient as possible in the ways I've just said. For example, But at the end, you bottom out at the depth that you've set, possibly going a little bit further if you've got some forced moves, as already described. And all you can do at that point is evaluate the position. So you want an efficient position evaluation because you're going to have to apply it many, many times to thousands of if not millions of positions. But at the same time, it wants to be a good position, a good evaluation. It's worth spending time on thinking about what a good position evaluation would be. Now, I'm not going to give you the secrets of my own position evaluation, apart from I've said one thing already, which is that it's essentially based on the groups and their liberties. But having been through these considerations for how to improve alpha beta, let's actually have a look at it in practice. So I'm going to run my game and make some commentaries on it. Maybe I should say there's one other thing, a surprising thing that I found actually made my alpha beta run faster. And that was when you have the list of moves to consider from any position, then I found it actually made the search faster if I randomized the order of the list of moves. So you'd think that takes a bit of time, randomizing the order of the list of moves and then going through them in a random order, and of course it does. But on the other hand, it seemed to me, and maybe I was wrong, maybe I didn't investigate this thoroughly enough, but it seemed to me that if I randomized the order in the list of moves, then alpha beta worked more efficiently. And my only explanation for this is that by randomizing the moves, one eliminates sort of biases in the ordering of the list of moves that mean that the optimizations of alpha beta don't work as much as they could possibly do if one gets the moves in a random order. I'm not actually 100% certain about this, but anyway, I found empirically in my program that the efficiency of alpha beta improved if I randomized the order in which the list of possible moves from a position is considered in the alpha beta algorithm. Okay, so we're going to go to the game now. So I have a board here. So this is my implementation. I want to choose algorithms here. So I've got alpha beta implemented, and actually what I'm going to run this against to begin with is alpha beta 1, which is alpha beta search with a depth of 1. So basically no search at all, just going immediately to the position evaluation of the positions of that one gets after making exactly one move from the current position. So basically the white here is going to play purely according to position evaluation, and black is going to play according to the alpha beta algorithm. And we'll see how they get on. Right, well, you see I've got some information playing here, so being displayed here. And what it's saying for alpha beta, it's saying what the dynamically computed depth is, which is 4, and it's giving the time that it's taking to compute the moves. So it was up to 0.9 seconds, and now it's decided at this point that it can go to a depth of 5 with this dynamically assigning the depth. And actually that took 12.7 seconds. So that's a lot more than 5 plus epsilon seconds. But such things I'm going to let go as long as they don't happen very often in the competition. My program computes the average thinking time per move for each player at the end. And as long as the average thinking time is less than 5 seconds, then that's going to be acceptable. So now alpha beta's going sort of taking still around 8 and 11 seconds. So alpha beta is black here, so that's the one with the adapted depth, and the position evaluation is white. So you can see that actually white looks like it's doing rather well here. Might even win this game, which is not going to be. Yes, white won the game. So that's not a good advert for the alpha beta algorithm. That almost never happens, but it does sometimes happen. So the way the let's run it again. And we'll see what happens this time. So it makes it look as though alpha beta is really totally useless in this case, but that's not the case. And it was defeated then because white luckily managed to take a lot of area without knowing that it was doing so. The plays are a bit randomized. So once again, alpha beta has gone to depth 5 and is now doing a deep, is now taking a lot of time again. But it will soon, that time will soon go down. So, okay, so it's just taken 5 seconds, alpha beta. And the one that's only doing position evaluation is now very badly losing this game. So it couldn't play in its own area. So now it has to branch out into black's area here, black's territory, so to speak. And I think black is going to be able to quite easily attack that. We're going to see black attack the group. So it's a bit embarrassing that just the position evaluation did so well in the first run. But on the other hand, it shows that it's actually not a bad position evaluation, the one that I've got. And I must say that in numerous runs of these two programs against each other, I think I have only seen that happen once before. So that's just the luck of the draw when one's actually videoing something and then the most unexpected thing happens. So here we are, we finished the game. Because white was only doing position evaluation, its average time to tenths of a second is 0 seconds per move. Alpha beta, it had some long thinking when it first moved to a depth of 5. And it never got off a depth of 5 because there was still enough moves left. But in the end, it's the total average time, the average time over all the moves for its moves, its thinking time was 2.9 seconds. So that's well within the acceptability for the competition. Right. Okay. So let's just play one more game just to just to see that. Well, we'll see. So white's got a very small area there, but now it's going to. Well, we'll see what happens. But I mean, I've really not seen the depth 1 program. Maybe more than once, but it almost never wins against so the depth 1 basically position algorithm almost never wins against the against the program that adapts its depth. And yeah, I've forgotten what else I was going to say. You can see that connectivity is very important to this position evaluation here. So both players are. So it looks like okay, so I'm not quite sure what went on here, but anyway, this time the alpha beta did with the varying depths, and then this time the depth got up to depth of 7. And once again, the average time was around 2 point something seconds, and this time 2.4. So once again, so this time the depth got up to 7, and once again the algorithm with the depth of search won over the position evaluation. But as I said, maybe taking the unexpected, one should take the unexpected victory of the algorithm just based on position evaluation, the depth 1 search, as actually showing that this is really not a bad position evaluation, this one that I've implemented. Okay, so that's suggestions for improving alphabeta. For the second part, I want to go to something completely different, which will address 2 possible issues that exist with the minimax alpha beta approach. So one is that the minimax and alpha beta is heavily dependent on having a good position algorithm. It seems that from what we just saw, that my position algorithm is really not position evaluation algorithm is not too bad. But anyway, one has to find one, and obviously it's very dependent on that. Another issue is that there's the problem of setting the depth of the search in order to fit the thinking time of the algorithm into the allowed time. So basically 5 seconds, although one's allowed to go over it on occasion as long as you keep the average down. So one's got 5 seconds per move, but the exponential growth of a search tree actually makes it hard to fully exploit the thinking time, because the difference in time between a depth of n and a depth of n+1 search is enormous. So at the start of the game, it's a factor of 80. So for example, if in my case with my alpha beta algorithm, the depth of 4 search, alpha beta with depth of 4 search for the first move takes about half a second. So, you know, that we've got 5 seconds at the disposal. We're using only a half a second, so we're only using 1/10 of the time that's available. But on the other hand, we can't increase the search to use more of the time available, because if we did a depth 5 search, it would take 80 times half a second, and that's going to be 40 seconds. So so that's way over the allowed limit. So these are 2 issues. In some sense, the first one's really the more important, because the dependent on the position evaluation means it's you know, position evaluation is very game specific and also very hard to tune. I mean, I seem to have luckily found quite a good position evaluation in my algorithm, but anyway, you know, it's quite an issue how to implement a good position evaluation. So what I want to introduce you to is a completely different approach, which addresses both issues. So this is called Monte Carlo Tree Search. It's a very famous algorithm, relatively recently developed from the 2000s. It addresses both the issues because no evaluation function is needed. It's basically a generic algorithm that you can apply to any strategy game, even also to games that involve aspect of chance in them, but we're not going to address that today. Anyway, so it's a generic algorithm, so applicable to any strategy game. And it also avoids this problem with the huge discrepancies between different depths in the search, meaning that you can't fully exploit the thinking time, because with Monte Carlo Tree Search, you can fully exploit the allowed thinking time, because it simply performs a kind of intelligent random exploration of the game tree, and it performs this exploration for as long as it's allowed to. So maybe I should put a comma here to separate out the phrases. And I'm sorry I've switched to English in the writing here. That's because I had these notes already available in English, and I mean, I modified them a bit, but I didn't want to rewrite them in Slovene. Anyway, I didn't have time to rewrite them, let's say. So for as much time as available, the Monte Carlo Tree Search will search the tree, and it does so in a sort of intelligent way, focusing as much as possible on parts of the tree that look promising, although branching out when necessary in order to look at further parts of the tree. And by this approach, you can basically tell it to stop at any time. So you can say, do this for 5 seconds, and then we'll see what you found so far, and we'll take that as the result. So you can fully use the thinking time available. So as I said, this was developed relatively recently. So the current form that's usually used of the algorithm, which is the basic form that I'm going to present now, I think it was developed in 2006. And this algorithm's been quite famous for a while, but it really came to prominence in 2015 because the Monte Carlo Tree Search was one of the 2 ingredients. It was combined with a neural network component in a very famous program, AlphaGo, which was an artificial intelligence program that played the game of Go and defeated the world champion, or one of the world champions at Go for the first time. Actually demolished them in a tournament in 2015. So this was one of the big progress points in artificial intelligence, when people really realized that it was going to artificial intelligence was becoming much more powerful than people had thought was going to be possible by this time. I mean, lots of development since then as well. Anyway, so Monte Carlo Tree Search is actually one of the 2 main components of the AlphaGo program. Right, so, once again, we've got this scrolling, uncontrolled scrolling. It's really annoying, and I don't know how to avoid it, but anyway, I can just go to the... Right, so what I want to do here is illustrate how Monte Carlo Tree Search works, and then I'm going to explain it to you so you might think about implementing it. And let me give a warning to those of you who've not got alphabeta working yet. So Monte Carlo Tree Search is a quite considerably more involved algorithm than Minimax and alphabeta, and you should certainly get alphabeta working before you try to implement Monte Carlo. If you haven't got alphabeta working by this stage, don't try to implement Monte Carlo Tree Search. Right, anyway, I want to illustrate how it's going to work. So what we do, we're at a current game state. Green is playing here. So it's abstract. We're going to have green and red rather than black and white, but green is playing here, and they're going to be needs to decide between a number of moves, and we're going to build a Monte Carlo search tree for the Monte Carlo Tree Search to work on. And the way it works is, well, we start at the node that we're going to play, and we look to see what the status of this node is. And at the moment, this node is not expanded. So it's just empty. So we expand it, and we look to see at what all the possible moves from this node are. So let's suppose there are only three moves, just for simplicity. So those take us to 3 red positions. But let's not put the positions in, actually, sorry, because all we've done at the moment is we've calculated that there are 3 possible moves from the first move. And it's actually good not to have the position here, because what this means is that none of these positions have been visited yet. When we're in a game position that enjoys the property that some of the positions that can be reached by one move have not yet been visited in the search, we randomly choose one of the positions that's not been visited, say this one. So we're expanding this node by randomly choosing this move. We see what position we're at here. This is red's. This is the red player's move. And then what we do is we simply play a random game. Once we've just expanded a node, we play a random game through to completion. So red plays a random move, green plays a random move afterwards, red plays a random move, green plays a random move, and so on until eventually the game is finished. And in the case of first capture, when a game is finished, it's either won or lost. So somebody will win this game, either red or green, this random play that we've got from here, and we make a statistic of that. So let's assume green won that game. So the statistic from the point of view of red, whoa, I want a thin pen here. The statistic from the point of view of red is that red has won 0 out of 1 game played. So from this position, we've played 1 game and red has won 0 of them. And we now, having played our game and gathered this statistical information, we go back to green. It's green's move. Sorry, it was green's move. And we've also make note of the statistics here, take note of the statistics here. So green, we've also played one game, sorry. And green has won 1 game out of the 1 game that we played. Okay, that's 1 run of the Markov tree search algorithm. And we're going to take as many runs as we have time for. So in the case of the algorithm in practice, that will be, if it's for the competition, that'll be 5 seconds of time for as many runs as possible in order to fill the 5 seconds. In our case, it's how much time I can spend on it in this presentation. I want to get obviously a little bit further also to illustrate the rest of how the algorithm works. So we're now back at the start. We want to do another run. We're in the position that we still have children nodes that have not been visited. So we randomly select one of those. We expand that node. We make a random play from that. And perhaps this time red wins that play. So red has won 1 out of 1 game played. And green has now won. Oh, the 1 could have stayed. Green has now won 1 game out of 2 games played. Okay, start again for the 3rd run. Randomly choose one of the children that's not yet been visited. There's only 1 child, so our random choice is irrelevant. It's random. It's forced to be that node. So we have a red node here. Again, we expand that node to find out what the game position is, and we play a random play from that position onwards, and we see what happens. And maybe again green wins this. So red has now won 1. So red has now won 0 from this node out of 1 game played. And green has now won 2 out of 3 games played. I'm writing the information about the number of games played in black to the green number represents the number of wins of the green node, the red number is the number of wins of the red node, and the black number is simply the number of plays irrespective of who won the game. So it's sort of neutral between players in a sense, which is why I'm writing it in black. Anyway, we've done 3 runs, so now for our 4th run, we're now in a new position, because now we're in the situation that we don't have any children nodes that we've not visited. We've visited all the children nodes, and when we visited all the children nodes, we say that the current node we're at is fully expanded. And when the node is fully expanded, then there's an algorithm for which node we choose to go to. And that algorithm is on the next page. And this is the first stage of a typical run of Monte Carlo Tree Search. So in a typical run, we're now on the 4th run, but this is the first stage we're going to see this first stage of the run. This is the first point that we're seeing this first stage of the run. It's called selection. If we're at a fully expanded node, so we've visited all children, so we're at some node, in the case that it's a green node, we're at a node and we've won W plays, so green has won W plays out of a total number of visits to this node, capital N here. And it's a fully expanded node, so all the child nodes of it, these have all been played. And so for each of these child nodes, they're all red nodes, of course. We've got, in this case, this node was visited N1 times and red won W1 of those. This node was visited N2 times and red won W2 of those, and so on up to the kth node. So this node was visited NK times and red won WK of those. Now what we want to do is choose which child to move to. And there's a very funny, very perplexing, if you like, formula for this. What you do is you pick the child node I, so WI here, well, not WI, but child node I, so child node 2 would be this one, child node K would be this one. Pick child node I to maximize a particular value. So at each node, WI, we calculate this fraction, the value WI over NI, but notice this is a green WI. So this by the green WI, what I mean by that is the number of wins that green has had from the red node obtained by move I. So for example, from W1, for move 1 here, green W1 will be the number of wins that green has had from this node. So the red W1 is the number of wins that red has had, and we've had N1 visits. So the green W1 is simply N1 minus the red W1, because all the games that red didn't win, green won. We don't have any draws in Capture Go, so if we're using this for Capture Go, there's that simple formula will do. If you do have draws, you might score them as a half for each player. So we calculate the number of green wins from the ith node by Ni minus the red Wi. And what this fraction is then, based on what we've played so far, it looks like the probability that green will win from the ith node. So we want the best nodes for green, so we kind of want to go to the node with the best probability for green. So So that's why we're maximizing the probability that green's going to win to some extent. But together with that, we take into consideration another factor, which has this more complicated formula, C times the square root of the natural log of capital N over little n sub I. So capital N here is the number of visits we've had for the parent node here. And little n sub I is the number of visits that the child node that we're looking at has had. So if we're in W1, it's the number of times we visited this. And the more time we visit this node, of course, capital N is going to go up by 1 each time we visit this node, and little n1 will go up also each time we visit this by 1 each time we visit this node. But because we're taking a natural log here of the capital N, which might be a much larger number than little ni, because n is the number of times we visited this node, so that's going to include all the times we visited all the other nodes, plus potentially a random play that we made from this node before we created any of these child nodes. So capital N is going to be a lot larger than little n sub I in general, but we're taking a logarithm here, and eventually, if we keep on visiting this node, then this fraction is going to get quite small, and when we square root it, well, the square root makes a small fraction a little bit less small, but still, eventually this is going to, the more times we visit this node, eventually this is going to become a smaller fraction compared with those other nodes that we visited less often. And so eventually this formula is going to lend some weight to the nodes that might have a smaller probability of winning, but which we've visited less often but we visited far less often from the current search. And this is going to encourage eventually the search to branch out to other nodes. And this whole formula here is multiplied by some constant factor, and that constant factor represents our willingness to branch out. So here, let me add some notes here. So where C, which is a real number, is a chosen constant, sorry, my tablet's responding very slowly because of the recording and Zoom session that I'm doing. So C is a chosen constant. A larger C encourages branching out. Encourages a broader search. So taking more of the breadth of the tree, and we're exploring the breadth of the tree more often. I'm sorry, it's so painful with the writing here, but anyway, I have to live with it. Smaller C, I'll write as little as possible. Oh dear, it's really, really bad. So smaller C encourages more focused search. And the theory of this formula is that if C is greater than or equal to square root of 2, then what happens is that, oh, that's really almost impossible to write. What happens is that Markov Monte Carlo Tree Search if you run it for long enough, which would be a very, very, very long time, it converges to the optimum strategy for the game. But it's a good theoretical property to have. It means that it's not, as long as C is greater than or equal to a square root of 2, if you run Markov Monte Carlo Tree Search for long enough, then it's kind of heading in the right direction, even if it isn't going to find the best move in the time that you've given it. If you run it for long enough, it would find the best move. So converges to the optimum strategy. That's a really nice theoretical result. And kind of the theoretical recommendation is that because of this result, because of this result, the square root of 2 is a good number to take for C. So in fact, in my program, I've taken the square root of 2 because you want your search to be as focused as possible, and that you don't want, the whole point is to avoid the search is you want to avoid the problem of alpha beta or minimax, that you're exploring the whole breadth of the tree all the time, although alpha beta does manage to mean that you don't do that on all occasions, because you prune the tree with alpha beta. But here we want the search to be kind of as focused as possible, so we're not exploring too much of the tree, as long as we know that it's sort of heading in the right direction. So C being the square root of 2 is kind of recommended, but you can tune that in practice. You can try higher numbers, and even if you like lower numbers, and see what works best. I didn't notice that much difference when I changed the values of C by some factors. So I've stuck with the square root of 2 in my implementation. Anyway, so this is the algorithm. So in my case, with C is the square root of 2, the algorithm is that that we pick whichever one of these nodes maximizes this value. And I do want to write something else here, so let's maybe put it in purple. 2 other things. So in the case of, or maybe I'll save one of them for later. And now I've forgotten what both of them are. That's anyway, we want to follow this formula. So we go back to our tree. Let's hopefully it'll let me page to it without running off. Oh, there we go. Okay, so now what we want to do is follow this formula based on capital N is 3. Little wi here is 0, little wi, little w1 here. The green w1 is 0 because the red w1 is 1. So green w2 is 1 because green won that game, and green W3 is also 1. And without calculating the formula, let's just say that the formula chose this node. So we go to this node, and we look at this node, and well, maybe this node's got. So this node is again unexpanded. So we haven't visited any of its children. So we see what the child moves are. Oh, I want this to be black. And I've lost my black pen. So here we go. Right. So we've got 2 possible moves here. We haven't visited either of them, but we just do the same thing we did before. This is an unexpanded node. So we randomly choose one of them. Suppose it's this one. It's a green node. And we do a random play out. So we play a random game. Green randomly chooses a move, red randomly chooses a move, blah, 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 all the way through until the game's finished. Sequence of random moves. We see who's won. And let's suppose that red won, no, the green won that game. So green, oh, yay. So green's won that game, so green has won. So it's won 1 out of 1 here. So green won that game, so red still won 0, and it's now out of 2. And green's now won 3 out of 4. Okay, so that was the end of the 4th run of Monte Carlo Tree Search. For the 5th run, we're again, so this is a fully expanded node. We visited all the children. So again, apply the same formula. Let's assume that, so now green's won 2 nodes here. So let's assume it again chooses this node. So this is the formula. Let's assume it again chooses this node. Once again, this has a child that's not visited. So we need to go to the node that's not visited, expand that. So, and play another game. And let's suppose and let's suppose that red won this one, and so now green's going to won 0 out of 1 here. So that's supposed to be green. I'm sorry, this is so slow. I'm really struggling with my drawing technology responding in a good, timely fashion. Okay, so red has won this one. So red has now won 1 out of 3. Whoops. And green has now won 3 out of 5. Okay, so we're at the end. That's the end of the 5th run. I just want to make that 5 a bit neater. So for the 6th run, we start again, and we're at a fully expanded node. So the algorithm the formula needs to choose the maximum value. In this case, I'm pretty certain it would choose this one, but let's pretend that it didn't, because I don't want to expand yet another node. I want to just look at a little bit more at the behavior as one gets deeper. So let's pretend that it didn't. Let's pretend that our selection algorithm chooses again the same node here. Then we get to another fully expanded node. So we again apply the selection algorithm, only this time this is a red node. So what do we do when we do the selection algorithm from, oh no. It's very frustrating. I need to find, the problem is the software only behaves like this when I'm doing too much on my computer at once, which I am now because I'm running so many programs at the same time, including the recording. Anyway, I'll stop making excuses for it. What I want to do is say we're now at a red node. Well, what do? Well, we maximize again the same formula, only we now swap the roles of red and green. So we're at a red node here, and we've got green nodes here. So we want to maximize red wants to move to the node that looks most promising for red. So it's going to maximize the formula using red WIs, calculated from the green WIs. These are green nodes, they'll have green WIs associated with them, and once again we'll calculate the red WI via the NI minus the green WI. So all I want to write here is, this was one of the two things I was going to write, but it's now a more appropriate point to do it because we're at that point in the search. So what I want to write is when selecting when selecting for a red node, it's really painful. Simply swap the roles of red and green. I hope nobody's red-green colorblind. It only just occurred to me that that might be a problem. Swap the roles. There's some little funny thing on the O there. Oops. Of red. Oh, it's so slow. And green. So apologies to those of you who are suffering through this very slow writing. I don't think you're suffering as much as I am. Okay, so, oh no, everything's going wrong. So here we are at our tree. You may remember, we've started our 6th run. We'd rather, I think, erroneously selected this node using our formula, which I don't think it would do, but anyway, we've pretended that it's going to select this node. And now we're at the red node, and we're going to apply the formula correctly, although I'm not going to actually calculate it. And applying the formula correctly, it's going to select the most promising node for red to look at. And that's of course, That's going to be this node here where red actually won its game. So we're again now at an unexpanded node. And you see the role of selection is to take us through the tree we've constructed so far. We select at each fully expanded node until we get to a non-fully expanded node, at which point well, this is a node we haven't even visited before, so we do all the same things we did before. We look to see, and this wants to be black. We look to see all the moves we've got available from here. We then, this non-expanded node, we pick a random child that we haven't yet visited. It's going to be a red one. So suppose it's this one maybe. And we play a random playout. Again, sequence of random moves until we finish the game, resulting in, let's say, a win from red. Whoops. So a win from red. Oh, that's supposed to be red. And it's won. Red has won one. Have one play. And again, we do what's, I'll give it its right name now. We propagate the statistic backwards. We do back propagation, updating the scores everywhere we go along, incrementing the number of games we played by one up the branch to the route we've just played, and on the red nodes, incrementing the score by one because red won this game. So this is a green node, so green's still only 1-0, but it's now out of 2. Oh, even that. Just completely unmanageable. That's a 2. Red has now won 2 out of 4 here. And green has won now 3 out of 6. Then if we were to do a 7th run, well, maybe it would really choose this one and expand this node and so on. But I think that is enough of the expansion of the tree, because we've now seen all the ingredients of Monte Carlo Tree Search, and I can tell you the algorithm in general. So on any run, you have 4 stages. The first stage is the selection stage, which applies when you're at fully expanded nodes. Then you maximize the child node according to the formula. So here's the formula. And maybe let's circle the formula. Oh, that wasn't a good idea. Things are so, joining up's going to be, oh, well, anyway, never mind. I'll do that offline. Anyway, maximize according to that formula. But for green nodes, for red nodes, you swap the role of red and green. And the goal of this, of selection, so selection finds a path from the root node from root to a non-fully expanded node. The node that is not fully expanded. you may know that in English, when you have a phrase that you turn into an adjective, so here I'm talking about a non-fully expanded node, which I could say numerous times in the time it's taken me to write it. When you have a phrase that's an adjective, using as an adjective, you hyphenate it. So anyway, selection finds a path from the root to a non-fully expanded node. And then when you get to a non-fully expanded node, so that means we haven't visited all of the children. So from a non-fully expanded node, you randomly choose one child that has not been visited and add that node to the tree. So here it's a situation, this node is not fully expanded because we've visited 2 children before, but we've got 2 that we haven't visited. So we randomly choose one of the unvisited nodes and add that to the tree. Once we've added a new node to the tree, so from the newly added node, we do the simulation phase, which is we play this random game. So a random move for the current player, then a random move for the other player, for just a sequence of random moves until the game's finished. This is called a random play out because you're playing out the game to its conclusion. And then we we play a random game, and there are some words missing here, which is going to be painful because I have to write them, and assign the node the relevant values. And assign, let me just write give, well, it's shorter. So the relevant values, so the statistics, who won the node, in this case green, who won the playout, in this case green, and we mark that this node has been visited once. And then there's the back propagation that we saw, that I named finally at the end, which is going back along the path to the root and update the scores to take account of the new game that we played. So incrementing all the black values by 1, and incrementing in this case the green won the game, so we'll increment all the green winning scores by 1. Well, so basically that's what you do in Markov Tree Search. That in Monte Carlo Tree Search, that's how it works. And this algorithm with these 4 stages, this describes every run of Monte Carlo Tree Search. How do we select the chosen move? So what we do is we end the algorithm after a fixed number of runs or after a specified time has elapsed. So in my program, I want everything to work within 5 seconds. So I end my algorithm after 5 seconds has elapsed. I do as many runs as I can fit into 5 seconds. And then having done that, I want to choose the relevant move. So how do we choose the relevant move? Well, you look at the results in the tree whose first level is, so this is the root of the tree. Maybe I should write that down. So it's the root of the tree. So this is the current, this is the play that we want, that we started constructing the tree from, the current move that we want to play. And for each of the children nodes, by the, we will have, assuming we've run it for any reasonable number of times, we're going to have expanded all these nodes and visited them many, many, many times. So we'll have statistics for all these nodes. Now each of these represents the winning. So here I'm marking down the green WI, so the number of times green has won, calculated from the red WI by NI minus the green. So NI the green one is NI minus the red one. So one thing you might want to do is just maximize the winning probability. But actually, the recommended thing to do is simply maximize the number of visits. So you pick the I that maximizes the node N, so you pick the child that has been visited the most often. In practice, because of the way the selection, the selection function works, that the selection formula that I wrote, in practice, this will typically maximize the winning probability anyway, at least to within some small epsilon. You're not going to be far off the maximum winning probability, but in almost all cases, it actually maximizes the winning probability. But the probability is not anything. The reason for choosing, not everything, the reason for choosing the score with the maximum number of, the node with the maximum number of visits is that actually one has, the more you've visited the node, the more confidence you have in the score you've assigned to that node. So the node with the maximum number of visits is basically the maximum winning probability, but we have the highest possible, we have higher confidence in that probability than we have in the other probabilities. So that's how we choose the moves. Okay, so that basically describes Monte Carlo Tree Search. So I'm trying to find, so I've implemented this in Java, and I'm just trying to get to the right page. So implementing this in Java, I simply use, the point is that you need to build this search tree with all the statistical information in. So at the start of the go, I start building my search tree and construct it dynamically as we go along. And I use basically a single class. For the main class for the tree is, the class is a class that an object of the class will be a node in the tree. And it's more, in my implementation, it's more complicated than this, but the essential fields of a tree node are, well, we have a field of class igre, so that represents at a node the game is in the current position, and this field value will be the current position of the game. You need to know what the potential moves from this node are, so what the child nodes in the tree are going to be. So I've got a field that's možné hypotéza, which is all the possible moves from the node. So again, možné hypotéza might be better. Well, anyway, for the moment, let's say all the possible moves. But in the case that there are forced moves, maybe you only need to have the list of forced moves here. Then we need to be able to, from a node, potentially access the children nodes. So I have a map that takes as its key a move and gives as its result another tree node, which is going to be the tree node that you can get to from the current node by making this the move given by the hypothesis field, by making that move from the current position. And I call this map otroci, because it's well, actually I don't in my implementation, but you could call it otroci because it kind of gives you the children of the node. And every node is going to have its statistic values. So I'm going to have a statistic for the number of, I hope the Sloven's correct, Število obiskov, the number of visits that the node's had, so the number of times we've been to that node and played a game through it. And then the Število zmag, so the number of times we've been to that node, and the current player, if it's a red node red, or if it's a green node green, the number of times that player has won the resulting play. And in my implementation, I use a hash map for the map and a linked list for the possible moves. It's not that important. So let's actually see this work in practice. So let's go to Java, and I'm going to keep my alphabeta player because we want to play against alphabeta. but I'm now going to play it against Monte Carlo Tree Search. And the van here is vanilla. So the vanilla means, in this case, without further embellishments. So this is the basic Monte Carlo that I've described, except that rather than looking through all possible moves, in the case that there are non ipotese, so in other words, that there are forced moves, it only considers the list of forced moves. That's the one difference I've made from what I described. I'm going to start a game here. So alpha beta is going to play relatively fast, apart from when it has a very slow move on occasion. Monte Carlo Tree Search is going to always take the full 5 seconds because I've programmed it to do as many plays as take. I interrupt it after 5 seconds. I finish it after 5 seconds, and we look at how many runs it's managed to see. So we play. Okay, and what we're going to see is there are very different styles of play. So here we have Monte Carlo Tree Search playing the oh dear, Monte Carlo Tree Search looks like it's going to lose. Everything's going as wrong as possible today. Well, look at that. That was absolutely terrible. So I'm going to start another game. But as you can see, Monte Carlo Tree Search is not doing very well. Okay, so this time alpha beta's played in a similar place to before, and Monte Carlo Tree Search seems to like playing on the edge and corners. Not really good play, but that's just what happens. And it's doing a lot of this. So you'll see that for Monte Carlo Tree Search, it's telling me how many runs it's had. So Pascusi means the number of runs in this case. The maximum depth it's got to in the search, the highest number of times it visited a particular node, and what it thinks its probability of winning is. And it's always taking 5 seconds. Alpha beta is taking. Okay, we've got a bit of a game on this time, and we'll see the different styles of play that alpha beta likes to play orthogonally. This is a result of the position evaluation I use. Whereas Monte Carlo Tree Search is not playing orthogonally, it's making a sort of completely different kind of pattern. That's just what it seems to find as the best moves to play, but it's not very good at realizing what the best thing to do is. Hopefully, yeah, it managed to realize it had to wriggle out of that corner there. Let's see if it keeps on realizing it needs to wriggle out. Otherwise, it's going to get trapped otherwise white is going to get trapped in the top left corner. Oh, it didn't realize it needs to wriggle out, so white has got trapped. So Monte Carlo Tree Search is not doing very well. Okay, alpha beta has won. So all that effort went into programming it, and Monte Carlo Tree Search is not doing very well. And in fact, I haven't managed to get it to do very well for this particular game of first capture, of capture go. But still, when you come, for those of you who come to program Go itself, Monte Carlo Tree Search is probably going to be better than alpha beta for playing Go. I haven't actually programmed Go yet. I'm going to make another little, much shorter video about programming Go soon. That's the plan. Anyway, before doing that, before finishing, I don't have much more to say, but it's a bit disappointing with regard to how Monte Carlo Tree Search is doing. I think one of the problems is that the position evaluation that I've got is just too good. I mean, we saw that it even works very well even without any depth of search. And Monte Carlo Tree Search is not using that at all. And moreover, this size of board, this 9x9, has such a large search space that in the 5 seconds, with the number of runs that my Monte Carlo Tree Search is getting, it's not really getting time to find anything approximating the best move. But I'm not going to take very much longer, but let's just make a little bit of effort to improve Monte Carlo Tree Search. So let's go back to the notes, and now I can't overshoot this time because it's the very last page. Oh, but I can get there and then not be allowed to see it. Send back again. Right. So various ways of improving Monte Carlo tree search. So one thing one can do is reduce the branching. So I already mentioned that when forced moves, that's what I was calling nune potesa, exist, only consider forced moves in the tree, and also only consider forced moves in the random playoff as well. So don't make the random playoff completely random. It should at least play a forced move when it has one. So actually that was already implemented in the vanilla Monte Carlo tree search that I just showed you, this little improvement. But the next thing was not implemented, and that's that also don't include suicidal moves in the tree branching, both in the constructing the tree and in the random playoffs, unless there is no other move available other than a suicidal move. So if it's a lost position and you have to make a suicidal move, then of course you need to have one such move in the tree. But what I mean by suicidal moves here are the direct suicide, where you play a move and that actually playing that move results in that stone and potentially some other stones adjacent to it that then belong to the same group immediately being captured. Or you get something else that's just as easy to detect for, basically, is playing into a position that so black playing into a position here that on white's next move, white would simply take that piece. So playing into a position that you can immediately be taken. So one can eliminate branching, so having unnecessary and bad branches in the tree by not considering suicidal moves. And so once again, both these recommendations can be implemented. So do this. So both in tree construction. So don't consider such moves in the tree construction. Oh, it seems to be writing better now. Don't know why that is, but it's very welcome, both in tree construction and in playoff, or the play out, rather, not the playoff, sorry, the play out, and in the random play out. Another thing one can do is make the play out more realistic. So if you're playing random moves, then if we go back to the game, then I've got a random player here, Nakluchno. If I play it against itself, then we can see what a random play out looks like. The random play out is, I mean, obviously just playing random moves. As you can see, it's basically just scattered all over the place. So they're just very scattered, no patterns at all. So such play doesn't correspond at all to anything like the play one gets in a game. So what I thought would be worth experimenting with is, without taking a lot of time over it, because you want your play out to be as efficient as possible, experimenting with a play that can be calculated efficiently that looks qualitatively a bit more like the kind of play that one gets in a game. So I've got what I call a guided play out here, which is some very simple heuristics for playing. And if I play the guided play out, you see it sort of tends to group the play together in groups a bit more. And it looks, qualitatively, there's no thinking time involved. It's still doing random plays, but following some rules for how to do it. And it looks a bit more like a typical play of the game. And I thought maybe if the random playouts are more typical looking, that might improve the efficiency of the Monte Carlo tree search. So I've also implemented that. And lastly, if we go back to the notes, another thing you can do is, well, once you've built your Monte Carlo tree search tree for, you've been trying to do one move, when it's your move again, sort of after your opponents had their move, you come back to your algorithm. Well, if you've got Monte Carlo tree search, you could potentially use part of the tree you've already constructed from the previous move, because you'll have already looked at the current game position on in your previous search, and you'll have already had some play going from it. So you can have a bit of a head start to the search from the current position. So you don't want to just accumulate the whole tree all the way through the game because and never get rid of anything, otherwise you'd end up eating up all your memory. But at the start of the current go, you could take your tree, you could store at least a tree from the previous go, you could take the tree from the previous go, copy the relevant portion of it over, and then start from there. And then you've got, as I say, you've got a head start on your search from the current position. At the beginning of the game, this head start's going to be tiny because it's going to be a tiny fraction of the original of the original tree, almost not worth doing. But as the game progresses and there are fewer and fewer moves, this should get, the tree will gradually get bigger and bigger, and this should actually should actually sort of help more and more as the game goes along. That's the theory. Only I haven't actually implemented this myself. So what I have implemented is the reduced branching with the not looking at suicidal moves, neither in the tree construction nor in the playout, and in using that guided, more realistic way of playing the random playout that I illustrated earlier. So let's go back to the game position. Sorry, not the game position. Let's go back to the game window here. And to end this presentation, I just want to see how, oh, it's terribly slow. There we go. How alphabeta is going to do against my, so I've got Monte Carlo tree search with 5 seconds. The constant is always the square root of 2. The vanilla one, NSU means without suicides, but without the guided playoff. The GPL is also without the suicides, but also without the guided playoff. So Monte Carlo tree search with all possible modifications. And let's see how alphabeta does against this, my best version of Monte Carlo tree search. So it's going to take a bit of a while because Monte Carlo tree search is always going to play every 5 seconds, but we'll see. Okay, so we're starting a new game. Alphabeta is taking 1.2 seconds for its first move. Monte Carlo tree search is playing like this. So it's actually playing. So because I've got so much working in the background, it's actually playing many fewer moves, but many fewer runs than it normally does when I play it against when I play it against the alphabeta. As you can see, it's adopting a rather strange strategy, building along the edge here. So Monte Carlo tree search seems to find that, and now it's playing dangerously close to black as well. So this may be a quick victory for alphabeta. So I have to tell you, alphabeta wins the majority of the games, but Monte Carlo tree search wins sometimes. So my conclusion from my experimentation is that, at least within the 5-second framework, Monte Carlo tree search and the way I've implemented it is not appropriate for first capture, but it is still the approach I would investigate if I were implementing Go. Anyway, we shall see. I mean, having said that, it's not Monte Carlo tree search has at least seemed to have wriggled out of its so far. Wriggled out. Well, let's see. It needs to connect now. If it doesn't connect, okay, it did connect, fortunately. So black, alpha beta is being quite aggressive here, but Monte Carlo Tree Search seems to have wriggled out of it so far. Let's see. And now black's threatening in that corner. Oh, that looked like a bad move by Monte Carlo Tree Search. I think black can capture Monte Carlo Tree Search in that corner. Black's taking a long time to think now. So it's gone up, it's just gone up to a depth of 5. And it's probably going to take a very long, it's taking a longer time than it normally does because I got so much. Well, so it took 21 seconds. And it seems to have allowed white, maybe it needed to do that. It seems to have allowed, it probably did. It's allowed white to escape from its tight spot in that corner. So this is turning into a quite reasonable contest, this one, except that alpha beta is taking much longer than it should, but that's because I've got Zoom running and the video recording running, and my formula for calculating the depth of search for alpha beta was done when I wasn't running so many background processes on my computer. So at the moment, it looks like anybody's game to me. Anyway, there's this different style of alpha beta playing these kind of orthogonal straight lines here, and Monte Carlo Tree Search playing sort of a bit more higgledy-piggledy. But now Monte Carlo Tree Search has played a very dangerous move. I'd be surprised if it can get out of that one. I think alpha beta should attack, and which it's doing. Let's see if Monte Carlo Tree Search can escape from that. Oh, doesn't look good at all. And in fact, alpha beta, its score's gone to 300, which means it's calculated it can win. Now it's got up to 500, which is winning sooner. And there we are. So alpha beta won that game. So that wasn't very impressive, but I mean, it wasn't a bad game. It's not as good as ideal a competition as it wasn't as balanced a competition as one would have had if the background processes hadn't been running, since that heavily affected Monte Carlo Tree Search, since I'm limiting it to 5 seconds of thinking time, but it didn't affect alpha beta because I'm still using the same formula for alpha beta that's calculated to work within 5 seconds in the case that I don't have background processes running. And but now I've got the background processes running, alpha beta is taking more thinking time than it should. And indeed, when we look at the end of the game, Monte Carlo Tree Search had an average thinking time, as it was bound to have, of exactly 5 seconds, whereas alpha beta actually was thinking for too long for the competition, 6.8 seconds. So actually alpha beta would be disqualified from the competition. When I run the competition, I'm not going to be running Zoom and I'm not going to be recording at the same time. So when we run the competition, we will be able to have a better battle with alpha beta fitting within its 5 seconds time slot, and the Monte Carlo Tree Search would be running I think about twice as many runs on each move as it was running this time. So that would probably lead to a healthier competition. Anyway, hopefully this has been much longer than planned, partly due to the difficulties I've had with the software. So anyway, hopefully there's something of interest in both halves of the lecture, and particularly, Monte Carlo Tree Search. Well, it may or may not be useful for for the first capture Go for the competition. But for those of you who are going to implement the full game of Go, then I really do think that that's going to be a promising approach to the intelligence to adopt. Okay, so that's everything for now. If you have any comments, please send them by email, or you can add comments on the YouTube to the YouTube video. Yeah, well, that's everything for now. See you hopefully next week for the last of the programming workshops.